Nuclear fusion is the process by which small nuclei fuse together to form larger nuclei. This is the process that fuels all stars, including our Sun. But what exactly happens in fusion, and why does it release energy? Let's begin by examining a helium-4 nucleus. Helium-4 consists of 2 protons and 2 neutrons. We know the mass of neutrons and protons, so let's do a quick calculation to find the mass of a helium-4 nucleus. We can take the neutron mass and multiply by 2, the proton mass, multiply by 2, and add them up. This gives us a mass for helium-4 of 6.696 times 10 to the negative 27th kilograms. But it turns out that's not right. If we actually measure helium-4, we find that it only has a mass of 6.45 times 10 to the negative 27th kilograms, less than what we calculated. We can compare these two and find that the amount of missing mass is 0.051 times 10 to the negative 27th kilograms. This might not seem like a huge amount, but this is a big deal for physics. This difference in mass is what physicists call a mass defect. And it turns out that every nucleus larger than a single proton has a mass defect. Why? To explain this, we need to turn to Einstein's famous equation, E equals mc squared. But we're actually talking about a missing mass, a changing mass. So let's rewrite this equation as E equals the change in mass times c squared. Let's examine this equation in a little more detail. Delta M is the mass defect, or the mass that is missing from our reaction. C is the speed of light, 3 times 10 to the 8th meters per second. That's already a big number, and squaring it makes that term even larger. E is the energy released in our reaction. This tells us that the mass defect, the mass that disappeared in our nuclear reaction, actually turned into energy. Mass and energy are equivalent. Let's consider the helium-4 we were talking about earlier. To form helium-4, how much energy is released? We calculated before that the mass defect was 0.051 times 10 to the negative 27th kilograms. Plugging in our value for the speed of light, we can calculate that the energy released by one helium-4 formation is 4.59 times 10 to the negative 10th joules. Sometimes this energy is called the binding energy because it is the energy given off as the individual nucleons bind together to form a nucleus. It's also the energy required to break a nucleus into its individual protons and neutrons. It turns out that this binding energy is very different for different isotopes. Let's take a look at some examples. As we compare the mass defect for these two elements, we will use the atomic mass unit as our unit of mass instead of the kilogram. It makes our calculations a little bit cleaner. You can see listed below the mass of a proton and a neutron in atomic mass units. In order to compare the mass defect for two elements, we will first of all need to know the number of protons and neutrons in the element, as well as its measured atomic mass. For nitrogen-15, we have 7 protons and 8 neutrons. For potassium-40, we have 19 protons and 21 neutrons. To calculate the mass defect for each of these isotopes, we will take the number of protons multiplied by the mass of a proton, the number of neutrons multiplied by the mass of a neutron. After adding these together, we will subtract the measured atomic mass. This gives us the mass defect for each element. How do these numbers compare? Well, the mass defect for potassium is almost 3 times as big as the mass defect for nitrogen. But potassium is almost 3 times as big as nitrogen. So to really compare these values, we actually need to go one step farther and calculate the mass defect per nucleon. That means that for nitrogen, we'll take its mass defect and divide by 15 because it has 15 nucleons. For potassium, we will do the same thing. Take the mass defect divided by 40. Now comparing the mass defect per nucleon, we see that potassium does indeed have a higher mass defect per nucleon. That means that as potassium was forming, more of its mass turned into energy. This graph shows the mass defect per nucleon for isotopes listed by mass number. The examples we've talked about are here: helium-4, nitrogen-15, and potassium-40. Remember that as we look at reactions moving from point to point on this graph, increasing the mass defect means mass is turning into energy, and energy will be released. So, changes that move in this direction are releasing energy while moving from a small to large mass number. This is fusion. And changes that move in this direction are still releasing energy because they're moving up on the y-axis, but they are moving from large to small mass number. This is a fission reaction. The point at the very top of this graph is the isotope that has the highest mass defect or binding energy per nucleon. Moving in either direction from this isotope requires energy instead of releasing it. This point is iron 56. One of the few places in the universe where the temperature and pressures are high enough to slam positively charged protons into each other is at the center of stars, our sun included. Our sun converts 4.3 million tons of mass into energy every second. It does this by fusing hydrogen into helium in its core. Stars that are larger and older than our sun fuse other elements. They fuse helium into carbon, carbon into oxygen and neon, neon into magnesium, oxygen into silicon, and finally, silicon into iron. All of this fusion within stars is actually critical to our very own existence. You see, in the first moments after the Big Bang, when particles finally cooled down enough to form nuclei, they formed a universe made up of about 75% hydrogen and 25% helium. Hydrogen and helium were the only two elements that existed in those first instants. All of the other elements were formed by the fusion inside of stars. The fusion of elements from helium through iron give off energy. These fusion reactions occur during the normal lifetime of a star, fueling it as it shines. But fusing elements heavier than iron actually takes more energy than it produces. These fusion reactions cannot sustain a star during its lifetime. Instead, all of these heavy elements fused in the huge supernova explosions that occur when a star dies. In the words of the 20th century astronomer Carl Sagan, the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, we are made in the interiors of collapsing stars. We are made of star stuff.